Okay, hello everyone, good afternoon and welcome to this session on special relativity. So my name is Martin Hendry and as Gregor's been welcoming everyone online, I've been recognising a lot of names, so I know there's some very familiar people to me out there and hopefully I'm reasonably familiar to many of you. But this is the first time I've done one of these sessions. I'm very much looking forward to it, and indeed if it does go well then there will be a sequel. The sequel might well be in a few months' time. We're going to try and do something on general relativity. It really would be a bit ambitious to try to cover both special and general in a single session. But I want to leave plenty of time for questions and discussion, so if people have any questions about general relativity, or indeed other aspects of the higher or advanced higher course, I'm happy to do my best to answer them. But by and large, we'll try and keep our discussion focused on the special relativity content of the higher. So I've called this Einstein's universe, and of course Einstein finds his way into many areas of physics, not just special relativity, but he's always been very close to my own heart. I'm Professor of Gravitational Astrophysics and Cosmology, so very much what I do is building on Einstein's legacy from the 20th century that really unearthed all manner of new phenomena in astrophysics that we're still trying to get our head around. And I'm reminded, and I thought I might begin by reminding you, that Einstein is of course such a major figure, not just in science but in all of society and culture. And a wee story that some of you might have heard me say before, but it certainly makes me laugh. Back in 1999 for Einstein's 20th century. Now there was a public vote and the public voted for Elvis Presley, but Einstein was the unanimous decision of the editorial board. And I think that's a sign of just how important his scientific and cultural legacy still is, even as we're well into the 21st century. And well, as Gregor can possibly spot it out of the corner of his eye, I've got my Albert Einstein action figure on my desk, so I'm constantly reminded every day of just how important Einstein has been in shaping my research and my career as a physicist. So we've celebrated Einstein a lot over the years. When I was a bit younger and a bit less experienced at Glasgow, one of the things that got me involved in schools outreach quite early on was the fact it was International Year of Physics, which in the UK we designated Einstein Year as well, because it was recognising the 100th anniversary of Einstein's so-called miraculous year, when he wrote a bunch of papers that really opened up special relativity, made revolutionary discoveries in atomic physics and quantum physics, which is the one he actually got the Nobel Prize for, the photoelectric effect. But as I said, we're going to focus here just on special relativity, but it's still quite appropriate to be doing a discussion on relativity in early 2016 because the centenary of general relativity is very much in full swing. The papers that represented Einstein's general theory really came out in 1915 and 1916. And I like to remind people, and no doubt many of you will realise this, that it's a sign of just how tricky general relativity is that it took Einstein 10 years to make the leap from the special theory to the general theory. So it's, again, no surprise that we should just restrict ourselves to the slightly more straightforward or slightly less unstraightforward special theory in discussing Einstein tonight. So what exactly am I on about when we talk about the special theory of relativity? Well, I've put up two slides. These are the only slides I think you'll see from me that I've got the words SQA in them, because I'm certainly not here as an official agent or official spokesperson for SQA, but for my sins, I was involved over the last 5 or so years in developing the content that now finds its way into the CFE Higher and Advanced Higher Physics syllabus, where we've introduced some elements of relativity to those two subjects. So if you look at the unit course notes, the support notes for the CFE Higher, well, there's a little table in there that lists the basic ideas and concepts that we're expecting to be taught now within the CFE Higher in the area of special relativity. So I'm not going to read these out, but basically the content in these three tables, including the rightmost one, the one involving those nasty formulae about time dilation and length contraction, that's what we're going to try to talk about today. So I've got some slides to really try and support a number, if not all, at least most of those bullet points in the content tables. But I've also got a slide that shows what's covered in general relativity. So you can think of this as a little bit of a trailer for our anticipated sequel session, and you can see there's quite a lot more in general relativity. It does of course build on what's already been covered in the higher, but I think the advanced higher, even though traditionally the advanced higher had some elements of relativity in it already, and that I recognise that it is quite a big ask to cover some of these concepts in the higher and then just a year later go on to more detailed concepts. Remember what I said a moment ago, if it took Einstein 10 years to go from special to general, then we want to help our students and teachers as much as we can to make that jump in just 12 months. So as I said, we'll look at special relativity today, but very happy to answer questions on aspects of general relativity if time allows us. So just before we get going in the physics, I thought it was worth to just make one brief remark about the why question. Why put relativity into the higher and the advanced higher in the first place? Now my PowerPoint numbering has malfunctioned here. This is supposed to say 1, 2, 3, but I suppose maybe the other way I can interpret this is that these 3 points that I've put there as my reasons as to why I think doing relativity is useful. I think these are all equally important, so maybe they do all deserve to be indicated as bullet point number 1. So the first one is just the fact that relativity is important in physics. We find it more and more in some of the topics that modern physics is dealing with. Everything from the big physics, the pure physics, the fundamental physics that we're doing at the Large Hadron Collider, which I know Aidan Robson has talked about in a similar session before, or the big physics that I myself am involved in searching for gravitational waves, and maybe some of you have picked up in the rumours that have been flying around about the work of LIGO. Well, I can't comment on those, we're still busy analysing like crazy, but let's just wait and see. There might indeed be some very important news there to report before too much longer. But there's also lots of applications of relativity in other areas of physics too, influencing much of the technology that we now have, everything from smartphones to atomic clocks. So that's one reason why we should be, I think, including more relativity in our higher and advanced higher. And I suppose another reason is that actually, unlike some other areas of physics, the maths actually isn't all that hard. I know you might say, well, that's easy for you to say, but I hope you would agree that the concepts might be tricky, but the maths involved is usually nothing more than Pythagoras' theorem. It involves working out lengths, working out lengths in particular of right-angled triangles, as we're going to look at in a few minutes' time. So if you look at other areas of modern physics, like say something like superconductivity, or even aspects of quantum physics, they're equally fascinating, but sometimes the maths can be much more challenging. So I think relativity is something that is, in principle, within the grasp of students doing the higher and the advanced higher, and you're not really compromising. You're not saying to them, well, we'd like to do it properly, but it's just a bit too hard, so here's a simplified version. What we're discussing in special relativity in just a few minutes is basically what Einstein did. It's exactly representing the kind of mathematics that Einstein embedded in his papers. And my third reason, which follows on from that, although the maths isn't too hard, as I said before, the concepts are very much harder. Sometimes the concepts are quite subtle. You're challenging students, and I'm sure you would all agree, teachers as well. You're challenging them to think very carefully about what we mean by measuring things, by measuring events, measuring the length of objects, measuring the time between events. How do we actually do that? And of course the spirit of how Einstein approached this was to think about experiments. He didn't necessarily do them. It's a bit hard to do experiments of things travelling close to the speed of light. But he came up with this wonderful concept of the thought experiment, the idea that you can make deductions and make often quite dramatic leaps of the imagination just by thinking about what the world would look like if you really could at ready. but I'm hoping that the way that I present it and some of the slides that I'm presenting in the PowerPoint, that perhaps you'll be able to use them yourself, or at least it will give us some food for thought and for some discussion a bit later on. So I'm going to begin where Einstein himself began, by thinking about the classical world of physics that he essentially inherited, the ideas that came from people like Isaac Newton, and indeed even before Newton, Galileo Galilei. So Galileo was, in a sense, the first relativist, because he was very interested in thinking about how the world looks from different points of view, from different frames of reference. And in the Galilean approach, he tried to codify this into some simple equations. So we see the Galilean transformation represented here by the axes. So we've got the black axes, which are undashed, and we've got the blue axes, which are dashed. And the blue axes are coincident with the black ones at time t equals 0, which is also t dash equals 0. But then the blue axes are moving to the right with velocity v, and that means that the coordinates measured in the blue coordinate system are going to be different from the black. And in this simple setup, it's actually only the x coordinate that's different. So the y and the z, and also crucially the time, are the same in both dashed and undashed coordinate systems, but the x dash coordinate is related to x by this simple expression that's really just using distance equals speed times time. So Galileo, for all this maybe looks a harmless enough equation to us, it was quite a leap forward in the time of Galileo to have this way of capturing algebraically what was going on when you switch point of view, when you switch to another frame of reference. The trouble is, it's not correct. But the other trouble is that you only begin to see why it's not correct when you're confronted with the situations we deal with in special relativity, when you're travelling close to the speed of light. Because the Galilean transformation works perfectly well for most everyday experiences. When I'm driving my car to the university from the south side of Glasgow, the Galilean transformation works just fine for me. And we see that if we move on to the next slide, where the kind of situation that as a car driver that I might experience, and I try not to think too much about Galilean transformations when I'm trying to drive to the university, because it would be a little bit of a hostage to fortune, all that abstract thought. But if you step aside from the mechanics of actually driving the car, what of course you see is that as you're overtaking a vehicle, that's me in my blue car overtaking the red car, then it looks to you, if you think of the blue car as stationary, as if the red car is reversing towards you and then continuing to reverse in your rear view mirror and going ever further away behind you. So this is just because, according to the Galilean transformation, we should be able to switch frame, switch point of view, so that in fact it's the blue car that's stationary and it's the rest of the world that's rushing past me in my blue car, rather than the blue car that's moving forward. Now, there are many situations where it does make a lot more sense for us to think about it as one frame rather than the other. Is that the rules of physics should work equally well in both frames. We should be able to look at how the laws of physics operate without being tied to one particular frame of reference. And that's really where it all started to unravel, the Galilean transformations, when they were confronted by Albert Einstein. But I'm a proud Scot, and I think it's appropriate to make the next step in the story not to jump straight to Einstein himself, but to take a few minutes to think about James Clerk Maxwell. Because the Galilean transformations, as I said, work perfectly well in most everyday situations. They do break down when you're travelling close to the speed of light. And in fact, the first person to appreciate what the significance of that speed of light was really James Clerk Maxwell. Astronomers had tried to measure how fast light propagated prior to him, in fact, round about the time of Galileo. There were various experiments that had been done. There was a very clever one done by Romer using the satellites of Jupiter, and he'd made the observation that sometimes the satellites moved into the sun's shadow a bit later than others. And he deduced that this was because the light was having to travel further because Jupiter was on the far side of the Sun from the Earth. So astronomers had a good idea of what the speed of light was as a number, but they didn't know very much about the nature of what light really was. And Maxwell came along with his theory in the mid-1800s of light as an electromagnetic wave. So where that starts to connect with relativity is in the notion of electric and magnetic fields. So the way that I like to think about this, it's a little bit of a simplification, but we're certainly not going to be putting all of Maxwell's equations into the higher syllabus anytime soon, if I've got any say in that. But I think certainly by the higher, people are thinking about electric and magnetic fields. That's one of the other big elements of the higher syllabus. And therefore, they've got the notion that electricity, static electricity, as the name suggests, is to do with charges which are stationary, static charges, whereas magnetic fields we generally associate with charges which are moving. So the trouble is, if you're trying to formulate the laws of physics in such a way that they look the same, regardless of which frame of reference you're in, then frankly, the electric and magnetic fields and the equations of Maxwell and Maxwell's deduction that light was an electromagnetic wave, that should look the same regardless of which frame of reference you're in. And that's where it starts to get hard, because in one frame of reference charges might be looking stationary, you would associate them with an electric field, so that means in another frame of reference they'll be moving, so you would associate them with a magnetic field. So how do you preserve the structure of Maxwell's equations in such a way that they look the same regardless of how you're moving? Now a related kind of side question is, how does light actually propagate through empty space in the first place? So that first question about the structure of Maxwell's equations and how you make them look sensible regardless of which frame of reference you're in, we'll come back to that in a moment. But let's think first of all about this question of how does light propagate through space. And again, it's probably a story that many of you are familiar with, but the basic setup here is that Maxwell had his theory of fluctuating electric and magnetic fields, which he associated with an electromagnetic wave. So I've got a couple of equations on there. They're way beyond the higher syllabus, but many of you I'm sure will remember them fondly from your university days. And what they denote is relationships between the spatial derivatives and the time derivatives of the electric and the magnetic fields. And the bottom line is, if you put these together, you combine those two equations, what you come up with is a wave equation. So that's really where Maxwell got this idea of the electromagnetic wave. Some of you might have seen Jim Al-Khalili do a very nice derivation of that on his TV show Shock and Awe a few years ago, which was about electricity and magnetism. Now, I think maybe there's an animation to be had here. Oh, no, it's not appearing. So what was supposed to appear in the mysterious red box is a relationship between the constants that we know as the permittivity and the permeability of the vacuum. That's epsilon naught and mu naught. Those two constants are related to the speed c, which you see in the two differential equations. So you've got a relationship between magnetic field and how it varies in space. That's the upside down triangle called del squared. Again, don't worry, way beyond the higher syllabus, but it's just to let you see that there's this relationship which looks like a wave equation, and within that wave equation the speed is where the c is appearing. So the 1 over c squared is 1 over the speed squared, and c is in fact equal to the square root of 1 over epsilon naught times mu naught, or 1 over the square root of epsilon naught times mu naught, same thing. So I mentioned a little moment ago that Maxwell was aware of what the speed of light that astronomers had measured, back to the work of people like Romer. And then what he realised as he was putting the theory of his equations together was that what drops out of them was not only that light's an electromagnetic phenomenon, well, in fact, I've really given the punchline away. Not only do varying magnetic and electric fields produce waves, but those waves propagate at the speed of light, the speed that the astronomers had found for how light travels. So he immediately thought, well, this has got to be important. This is telling me that light is, in fact, an electromagnetic phenomenon. Now, This has been a little bit of a digression. It's driven partly by the fact that I'm always on a mission to make Maxwell's name a bit better known, and if I'm allowed to indulge in 2 minutes of shameless publicity, many people on Sputnik had already very kindly said that they liked the programme about James Clerk Maxwell that was shown on BBC Two back in December. But if you missed it then, I believe it was on BBC Four last night, so you can catch it in the iPlayer. And that was looking at Maxwell's legacy to do with electromagnetic phenomena. So let's try and now bring it back to Einstein. So we've got ourselves a wave equation for light, and Maxwell's eureka moment was the realization that those waves propagate at the same speed that astronomers had deduced for the speed of light. So light was an electromagnetic wave. But how's that going to sit in the world of Einstein? How's it going to sit in a world where you're trying to make sense of the laws of physics? They should look the same regardless of which reference frame you're in. So in particular, if you're talking about the speed of light, well, what's it with respect to? The speed of light with respect to what motion? Or another way to put the question, a related question, is how does light actually propagate through space in the first place? So for decades after the time of Maxwell, this was an unsolved question. And around the turn of the 20th century, the prevailing view was that light ought to propagate through something, and the popular idea was that there was a substance called the luminiferous ether. So it was a little bit like a kind of deus ex machina, you know, a god from the machine. Since we didn't really know what it was, well, we'll just call it the ether. But there were still some very clever physicists trying to see if we could somehow prove that it was there. And one way that was thought of was to look for the motion of the Earth through the ether. So if light is propagating through the ether, then that means if you look at stars in different directions, then the propagation speed of light from those different directions might wind up looking different to us because the Earth itself is moving through the ether. So my diagram's trying to capture that, and basically Michelson and Morley, they tried to devise an experiment to see if they could measure that speed of light coming from different directions. So the next slide tries to give an analogy for this, which again many of you have probably heard before, but to think of swimmers trying to swim in a fast flowing river. So we could have the swimmers swimming in the same direction as the river is flowing, that's from A to B, and then reversing their direction and going back again and swimming against the river flow. Or you could have swimmers going from B to C and back, which means they're neither swimming in the same direction as the river nor against it, but they're swimming across the river flow. And if you do the maths of this, just using the ideas of the Galilean transformation, if the river's flowing at a certain speed v, then you should be able to deduce what that speed is by looking at how long it takes the swimmer to go from A to B and back, and compare that with how long it takes the swimmer to go from B to C and back. So that was the type of experiment they set up. They were looking for a change in the arrival time of the light waves back at B, one beam going one way, one beam going the other, perpendicularly, and of course you would hope to see that as a change in the phase of the light, a kind of an interference pattern like what we look at in experiments like Young's slits. So the experimental apparatus for its day was pretty sophisticated, and in fact Albert Michelson was the first US winner of the Nobel Prize for Physics. So he was a top-notch experimental physicist. But in fact their experiment didn't work. Well, you could argue it did work, it gave a very important result, but it certainly didn't give them the result they expected. The result it gave them was that they detected absolutely no ether drift, meaning that it didn't seem to matter which direction you looked in, the speed of light was always the same. Light arrived at the Earth, seemingly propagating at the same speed through empty space. In fact, that rather suggested that space was indeed empty, that there wasn't an ether. Or at least if there was something else very weird going on that made the speed of light look the same in every direction, completely contrary to that example of the swimmers going against or across the river flow. So light wasn't following Newton's rules or indeed Galileo's rules, the rules of the Galilean transformation. So I think it's time to get back to Einstein now and start to look specifically at some of those bullet points in the special relativity content table. So Maxwell is putting forward this idea of light as an electromagnetic wave. It doesn't seem to propagate through an ether, or at least not in a way that manifests itself as having a different speed depending on the direction. And then we've also got this problem that if it's to do with varying electric and magnetic fields, and you now change your frame of reference so that, for example, you could make an electric field look like a magnetic field and vice versa, then how do you make Maxwell's equations hang together? How do you make it so that Maxwell's equations which frame of reference you're in? So that was really where Einstein was starting from. And in fact, he had a beautiful talent for capturing these sorts of ideas in a very simple way. He would ask the kind of questions that other people would think, darn, why didn't I think to ask that? So one way he asked this in this context was, he said, what would happen if I travelled alongside a light beam? Would it still wave? Because if you're keeping up with the wave, then would it be a wave then, because you would be travelling alongside it, and therefore it would just be frozen? Well, that's again kind of how it would emerge if you tried to apply the rules of Galileo's transformations. Or maybe another way to think of this, again an analogy that you've probably encountered before as well. If you imagine a train going at 50 miles an hour along the train track, and then it shines the lamp on the front of the train ahead of it, according to the Galilean rules, then the speed of light measured relative to the ground, to an observer alongside the train standing beside the track, that speed of light should be faster than the speed that you would measure on board the train. You would measure whatever speed you would measure on the train, but you'd have an extra 50 miles an hour because of the motion of the train. That's what Galileo's rules would say. But if that's really how things are, then you get into all sorts of trouble when you start to look at Maxwell's equations. When you change frames of reference, you move to a frame of reference where you're travelling very fast compared with another frame of reference, then Maxwell's equations lose their beautiful structure. And all of that prompted Einstein to acknowledge in the very first sentence of his groundbreaking paper on special relativity that he published in 1905, it caused him to acknowledge the debt that he owed to James Clerk Maxwell. So I know this is maybe a bit hard to read in the PowerPoint slide, but he name checks Maxwell in the very first sentence. Okay, it was originally in German, so I'll put the English translation up here. But I think, again, it just emphasises what great legacy we have in the science of James Clerk Maxwell. So the reason that Einstein did this is that he was setting out to explore the consequences of Maxwell's equations continuing to work in another frame of reference. So he wanted Maxwell's equations to still have the same structure, to still make sense, even if you transform to a different frame of reference where you're moving at a very different velocity. And what that led Einstein to conclude, which he spelled out in this groundbreaking paper, just a few pages, but what it led him to conclude is that in order to preserve the constancy of the speed of light, which was a crucial step in making Maxwell's equations work in another frame of reference, what he had to sacrifice was the notion of absolute space and time. So measurements of space and measurements of time depend on what frame of reference you're in. And that really is where the whole relativity story starts to open up. So as soon as you've got this notion of the relativity of space and time measurements, it means that really what you've got to do is not talk about space measurements and time measurements separately, but look at them together. And you've got this notion of space-time. Now the higher syllabus only just scratches the surface of this. We've tried very hard to keep the maths straightforward, like I said, just at the level of Pythagoras' theorem, as we'll see in a moment or two. But it leads on naturally to the need for actually a new form of maths as well. Well, it wasn't entirely new because mathematicians had come up with it in the 19th century, but Einstein didn't go to those lectures, so he had to rely upon his good friend Marcel Grossmann to help teach him the maths that he would need to understand this unified space-time, in particular in the case where you consider accelerated motion. Again, rest assured, that's not in the higher, there's just a tiny bit of that in the advanced higher, and again, without all the complicated maths. So we're talking about unified space-time, but we're still just talking about frames of reference where you're moving at a constant velocity. But even that is enough to just revolutionise many of our ideas about space and time, and also about matter and energy. So in a later paper that I think wasn't published until early 1906, but he submitted it in 1905, Einstein also came up with his famous E equals mc squared. So that's all background. I maybe took a bit longer on that than I planned, but it's letting us see where Einstein was starting from. He was looking for a way to make the laws of physics work regardless of how you're moving, and in particular to make the laws of James Clerk Maxwell work regardless of how you're moving. So let's try to see why going at that led Einstein to the conclusion that absolute measurements of space and time simply don't exist within our universe. Instead, they're relative to how you're moving, and only if you consider space and time together can you arrive at concepts of what truly doesn't vary from one observer to the other. So let's try and see why. Now, as I mentioned near the beginning, the way I'm approaching this is probably, well, I certainly hope it's useful, but it might indeed be very similar to how you yourselves have been approaching it in teaching. But I've just put some very simple slides together, and I've tried to look at it from the point of view of an observer on board a train and an observer on the platform watching that train go by. So the height of our train carriage is h, and what we're going to do is we're going to do an experiment where we shine a torch from the bottom of the train carriage, bounce it vertically off the roof of the train carriage, and then send it back to the bottom again, send it back to the floor. So on board the train carriage, that torchlight, that beam, has travelled a distance, just using distance equals speed times time, that we can write as 2h, which is the speed of light as measured on board the train carriage, c, times the time it takes the light beam to get there and back. So we'll call that t with a subscript c. So our basic equation, just using distance equals speed times time, is that from the point of view of a physicist on board the train carriage, 2h equals c times tc. So now let's look at how this would appear to an observer on the platform as the train goes past. So I wanted to avoid any fancy animations, so I'm just going to do this manually. It's just a series of still images in my slide, but there we've got our train going past. So very low-grade animation, but nonetheless, hopefully you get the idea. So let's just look at a couple of snapshots. So first of all, from the point of view of the observer on the platform, I've now got a diagonal arrow because there's two events that are important here. There's the event when the light beam leaves the floor, and there's the event when the light beam arrives at the ceiling. But in the time it takes that light beam to make that journey, the train has moved, and that's why that arrow is now pointing diagonally instead of vertically. And then the same thing happens, of course, on the downward part of the journey. The second part of the journey of that light beam, as seen by an observer on the platform, follows a diagonal path between the two events, the event when it bounces off the mirror in the ceiling, and then the second event is when it arrives back at the floor. So let's call the time that it takes that light beam to make that two-legged diagonal journey, let's call that time t subscript p, t platform. So we'll just put the three crucial snapshots together now. In fact, I've added a bit of detail. We've now got lamps and mirrors, but it's still, even by the standards of ScotRail, it's still a fairly frugal-looking train carriage. But you've got a lamp, you've got the mirror, and then you've got the lamp again, because it's the same lamp, of course, but the train has moved during that time. So this is as it would be seen by an observer watching from the station platform. So we've now got to do a little bit of maths. So viewed from the platform, I've just shown that diagonal path, but not stretched out quite so much, just to make it easier to fit on the slide. So let's call the time as measured in the platform t subscript p, as I said. So what we also have to consider is how that relates to the speed of the train. And we just use distance equals speed times time. The speed of the train, as measured by the person on the platform, is v. So the distance that the person on the platform would see the train move between those two events, it leaves the lamp and then it returns to the lamp, that distance is v times tp. So the base of the triangle is vtp. Now it's an isosceles triangle just because of the way we've set this up, and it's moving at a steady speed. So it's made up of two equal right-angled triangles. So there they are. And let's just look at one of them because the other one's just a mirror image of it. What's the length of the base? Well, that's quite easy because it's just half the length of the isosceles triangle. So it's half v times tp. What about its height? Well, back to what we started with. We called the height of the carriage h, and we said that h was equal, well, 2h was equal to c times tc, because that was the speed of light as measured on board the train times the time it took the light beam as measured on board the train to go from the floor to the ceiling and back again. So 2h equals c times tc. There we are, there's the torch beam reflected off the roof of the carriage. And that means, therefore, that h is a half c times tc. So now we've got to use Pythagoras. And this is the bit where we use Einstein's big idea. So Einstein's big idea, which I motivated before by connecting it to the work of Maxwell, Einstein's big idea was that the observers, regardless of whether they're on the platform or on board the train, measure the same speed of light. Now sometimes in books about relativity that's just produced almost like a rabbit out the hat. You know, Einstein just came up with this. But I think it's really important, maybe all the more so here in Scotland, to emphasise that he didn't just produce that out of a rabbit out the hat or out of thin air, whatever metaphor you want to use. Instead, he was doing it for a very specific purpose. He was doing it so that James Clerk Maxwell's equations would make sense to any observer in any what we call inertial frame of reference, a frame of reference moving at a constant speed with respect to other inertial frames. So, okay, I've done my Maxwell Appreciation Society bit, but let's just now look at what the consequence of that assumption was. So the total distance, if you measure the same speed, is going to be c times the time that you would measure on the platform. So we've now got algebra to tell us about all three sides of a right-angled triangle. And thanks to Mr. Pythagoras, we know how these three algebraic expressions have to be related. So we can multiply through by a half, get rid of the common factor. In fact, we can do another bit of simplification, basically tidy up the equations, but I've done it in a couple of steps. So first of all, we just take ctp squared is equal to vtp squared plus ctc squared. And then if you rearrange all of that, you get the formula you see in the red box. That the time as measured on board the carriage is equal to the time as measured from the platform times this factor, the square root of 1 minus v squared over c squared. Again, as I'm sure you're probably all very well aware, this is really the reason why the Galilean transformation works perfectly well for everyday life, at least everyday life when you're driving blue cars and that sort of thing, because v is so small compared with c, typically, at least the way I drive, that really you can neglect that factor for many practical everyday situations. But when v gets close to the speed of light, then this becomes an appreciable correction factor that means Tp is simply not the same as Tc. So to the observer on the platform, it looks to him or her as if time is running more slowly than to the observer that makes the measurement on board the moving train. Now the form that we often see this in, maybe more typically see it in, is where we just rearrange the equation and we put the time on the platform on the left hand side. So now we've got TC divided by the square root of 1 minus V squared over C squared. And I've done it this way so that we can link it back to what's, oh I'm sorry, I seem to have missed a slide. Here we are. So that we can link it back to what appears in the list of equations. So this is the table, it's just taken straight from the table of formulae and equations for the higher. And in that table, T dash is the time interval between events as measured in the platform frame, and T is the time interval between events as measured in the carriage frame. So T dash is what I was earlier calling TP, and T is what I was earlier calling TC. And then we've got our 1 minus V over C squared factor square rooted on the denominator. So that's the equation you've got in the content tables. It's the equation that appears in the formula sheet, and the derivation of that equation can be done using trains going through platforms and using this key idea that Einstein assumed, motivated by the theoretical implications for the work of Maxwell, that the speed of light would be the same in any frame of reference. It would be measured to be the same. Now, of course, what this also does is neatly explain why the Michelson-Morley experiment got the result that it did. Because had it given them the result they expected, it would have been because the speed of light did depend on how you were moving, whereas Einstein's relativity says that it doesn't. But as a consequence, intervals of time, and as we'll see in just a moment, intervals of space, do indeed depend on how you're moving. So let's now talk about that idea of intervals of space. A very common question, which I remember asking myself when I first encountered all of this many, many moons ago, is why can't I think of the train as stationary and the platform that's rushing past? There's a wee story about Einstein going to a conference in Oxford, and allegedly he said to the conductor, "What time does Oxford reach this train?" And the conductor probably thought he was a bit mad, but in a way it sort of makes sense. If you're sitting there on board a train and it's moving nice and smoothly, you can think of yourself as the one that's stationary, and then it's the rest of the world that's rushing past you. Or you've maybe been on the Glasgow Underground trains where you can have that experience. You're on board the Underground train, there's one on the other platform, and for a moment you're sometimes not very sure if it's you that's moving or the other train that's moving. So in the context of relativity, the result we've just derived would then start to look kind of strange, because if we start off by saying it's the train that's stationary and the platform that's rushing past, exactly the same analysis would mean you would deduce that from the point of view of an observer on board the train, then it's the clock on the platform that appears to be running slowly. And that seems weird. I mean, it felt weird to me, it still does at some level. How can it be that both observers will see the other clock and think that the other one is the one that's running slowly? It seems to violate some kind of conservation principle, you know, that things can't work that way both ways round. But the key to understanding why it works is when we remember that you can't just look at time on its own without also considering space. So another aspect of the content tables is to look at evidence for this so-called time dilation effect, this slowing down of time as seen from the point of view of another reference frame, to look at evidence not just from trains going through platforms, which, let's face it, don't go that close to the speed of light, but from particles that really do, and hence provide very strong observational evidence that Einstein was in fact correct. So a good example is the muon. So what can happen is that muons get produced when much more energetic particles, cosmic ray particles, things like protons coming in from out in deep space with enormous energies. There's some quite scary statistics here. The highest energy proton that's ever been discovered has got the same kinetic energy as one of Andy Murray's serves. So when you think how low in mass a proton is compared with a tennis ball, That really makes you think. So those cosmic rays, when they collide with our atmosphere, can produce showers of muons. And then those muons zoom off and they can reach sea level. We can measure them arriving at sea level. Typically this happens about 60 kilometers up. That's as measured in our frame of reference. So what's going on? Well, the reason this is a puzzle is that slow-moving muons should really never reach sea level because their half-life is about 2.2 microseconds. Now, if they're travelling at the speed of light, which in fact they are, they're travelling very, very close to the speed of light, then because the slow-moving muons allow us to measure their half-life from experiments we can do at the ground, if they had the same half-life, even though they're travelling at the speed of light, then they should only travel about 6 kilometres. Would be a factor of 10 less. If you multiply, that's roughly how far you'd expect to travel. Oh, sorry, let me do this in my head. I should have checked. No, I think it's 600 metres actually, so it's even less. It's a lot less than 60 kilometres. So, what's going on? So, the way that we understand this is that the muon is travelling very close to the speed of light. So it's only able to reach the ground because to us, its lifetime is greatly extended. So it's just like the person on the platform observing the clock on board the train appear to run slow. We appear to observe the clock, the built-in clock within a muon, which determines how long it lives for. We determine that clock to run slow, such that the muon survives for long enough to reach the ground. So now we come back to our paradoxical question, this puzzling question, well, why can't we look at it from the muon's point of view? So let's do that. In the muon's point of view, the muon isn't moving. Instead, it's the sea, the ground, which is zooming towards it at 0.999 of the speed of light. So in the muon's frame of reference, its half-life is still only 2.2 microseconds. But from the muon's point of view, it's the distance which the muon travels, which is much shorter. So in fact, in the muon's frame of reference, the muon doesn't have to travel for 60 kilometers to reach the ground. It's got to travel a much shorter distance. So even though its half-life is only 2.2 microseconds, it can survive that long. So we call this length contraction, and it's very much going hand in hand with time dilation. So we've got another equation from the equation sheet. L prime equals L times the square root of 1 minus V over C squared. So whereas in the T equation, the square root term was on the denominator, this time it's on the numerator. So we call this length contraction, and it says that from the muon's point of view, the space interval between events, that's the creation of the muon and the muon reaching the ground, the space interval between those two events as measured in the muon's frame is a lot shorter than the 60 kilometers, the L, that we measure in our frame. That's the space interval between events as measured in our frame. So that's how you can make sense of this reciprocity, this when you switch frame from one frame to another, that the deductions of Einstein still hang together. So you can't look at time dilation without also considering length contraction at the same time. So I'm nearly done. I have taken a bit longer to get through this than I thought, which I think does emphasise that including general relativity would have been a step way too far for one session. But we've still got a wee bit more head scratching to do, because actually what we're now touching on is what people often refer to as paradoxes. So one paradox is really what I've just gone through, that if you naively think, well, can't I just switch frame to the moving train and say, well, I'm in the train from my point of view isn't moving, it's the platform that's moving, then I would see the platform clock is running slow. So what's going on there? Well, there's other ways you can capture those same ideas, those same apparent paradoxes. One's called the pole in the barn paradox, another one's called the twins paradox. And usually making sense of them, is all to do with taking a step back and thinking really carefully about what we mean by simultaneous. Measure a length in relativity, you've really got to measure that length, both ends of the object at the same time. It's what we call the proper length. It's the length that you would measure if you were in a reference frame which is travelling along with that moving object. So it would look to you as if the object wasn't moving, so you can quite happily measure the position of each end of the object, and you can get what in some sense is its true length. But if you try and do things like that when you're in a different reference frame, then what you run into is the difficulty of how you make the measurement in space at either end of the object at the same time. You can't be in two places at once. Believe me, I would like to be, but it's a trick that we haven't mastered. Photons seem to be able to do it, but that's a whole other story. We'll leave that to the quantum physicists to ponder. From the point of view of relativity, you can't be in two places at once, and that's usually where these paradoxes come from. So let's just end by briefly considering them. Now, technically, to do it fully, in fact I didn't refer to this, but I wrote in the slide, details really lie beyond the scope of the hire, but I think they're interesting and they do segue very neatly into some of the things that you'll need for the advanced hire. So again, think of this as the the big cliffhanger at the end of the first film that's setting the scene for the sequel, which is going to be a session on GR. And it involves what we call space-time diagrams. So space-time diagrams for special relativity. You might still find this useful in teaching the special relativity content, but you don't really need it. But I think for teaching general relativity, then they can be very helpful. For special relativity, where we're just moving at constant velocity, the space-time diagram neatly divides into what we call the causal past and the causal future. Something called the light cone separates those two, and these denote regions of the future and regions of the past that events can influence or be influenced by. That's where the word causal comes from. You've always got to be careful with Microsoft spell check because it quite often comes out as casual future and casual past. But I checked this time and it's come out right. So a very simple space-time diagram we're going to try and use to just address very quickly and briefly these two paradoxes. So the pole and the barn paradox. So the idea here is you've got a pole that's say 20 meters long and you've got a barn that's 10 meters long. So those measurements are made in the same frame of reference. But now your pole starts to travel towards the barn at 90% of the speed of light. So that factor, the one involving the square root, we call it the Lorentz factor, sometimes denoted gamma, it turns out to be 2.29. That means in the frame of reference of the barn, the pole will look 2.29 times shorter. It will be length contracted. And that might naively make you think that you'll be able to now fit the pole inside the barn, because 8.73 is less than 10. Now that starts to look a bit paradoxical, because you can do what we did a moment ago. You can flip the reference frames round and you can now say, from the point of view of the reference frame of the pole, it's the barn that's rushing towards the pole at 90% of the speed of light. Therefore the barn should be length contracted, so instead of being 10 meters long, it's now only 4.37 meters long. So how can you at the same time have a pole that fits inside the barn and a barn that fits inside the pole? That's where the paradox comes from. Surely that can't be true. Now how you resolve it involves these space-time diagrams. So again, forgive me if this is a bit complicated, as if what I've been doing up until now hasn't been, but if this is a new, fresh level of complication, well, you can just zone out for a couple of minutes. But if this is a troubling problem, this pole in the barn problem, or maybe if it's something one of your pupils has asked you about, then this I find quite a helpful way to try and make sense of it. So what we see here is one of these space-time diagrams from the barn's point of view and from the moving pole's point of view. So we've got two frames of reference. They're colour-coded, one is blue, one is red. So if we think of the barn as stationary, then what we call the world line of the barn doors are just vertical lines because they stay at the same position in space all the time. The barn isn't moving. The pole is moving in the barn's frame of reference. So if we look at the ends of the pole, those are events that wind up having different positions in space and time in the barn's frame of reference as the pole moves. But we can also look at it from the barn's point of view, from the pole's point of view. That's the red lines. Now that's a different reference frame, and that's where the diagonal slanty stuff comes from, because we're transforming using Einstein's rules and not Galileo's rules. So that bit really does lie beyond the scope of the course, but it is how things are. It's when you do the time and length transformations, then it makes the axes slanted. And that's how we resolve the paradox, because look what I've said in the words. I've said that if you look at one instant in time, which is the horizontal line, the dashed blue line, that's the instant in time when in the barn frame it looks as if the pole lies inside the barn, because the ends of the pole, well, the barn door is event A and event, it's not event A, the ends of the pole are event A and event B, and I'm trying to point them out with the arrows because I realise I've maybe not put them clearly enough on the diagram. A is the point where my arrow is here. It's on the red line, the intersection of the red line and the blue dash line. It's the moment in the barn's frame where that end of the pole is inside the barn. And at that same moment, in the barn's frame, it looks as if the other end of the pole is inside the barn. Well, in a way, that's as it should be, because remember we said in the barn's frame, as the pole rushes towards the barn, it looks as if the pole is shorter than the barn is. So from the barn's point of view, it should be possible to fit the pole inside the barn. The trouble is, though, that's not really what's going on. That's just how it appears to the person in the barn's frame. Because if you ask yourself what's happening at that same instant in the pole's frame, well, that's where it all starts to unravel. Because those two events, A and B, which are at the same instant in the barn's frame, they're not at the same instant in the pole's frame. Because instead, in the pole's frame, A and B happen at different times. Because in the slanty axis, what's happening is, as we go to different times, those are different diagonal slants through this diagram. And if they're at the same horizontal level, they can't be at the same diagonal level. Told you this slide was a bit complicated. But ultimately this resolves the pole in the barn paradox. And again, probably, if you're getting questions about this, it might be unwise to go too deeply into all of this. But I've got a slide right at the very end, which might be a useful book to direct your Bright Spark students to. If they start asking awkward questions about poles and barns, then tell them to go away and read How to Teach Relativity to Your Dog. And I'll come back to that right at the end in just a few minutes. So before we stop, I just wanted to say something very briefly about the twins paradox. Apologies if I've ran over the time people were expecting. And I do want to leave a little time for discussion. But let's just wrap up in a couple of minutes on the twins paradox. You probably know the setup. You've got two twins called Terence and Stella here. They're both aged 20. Stella sets off in a spaceship to Pollux, distance of 33 odd light years, travelling very close to the speed of light. So from Terence's point of view, Stella's journey takes 33 years and 9 months. But from Stella's point of view, because time is flowing more slowly, then only 18 months elapses. And then after a few days over there at Pollux, Stella comes straight back again. And when she gets back, only 3 years have elapsed. That's 2 times 18 months plus an extra few days. Meanwhile, her twin Terence is now 87.5 years old. So what's going on? The reason this is sometimes called a paradox is that a little bit like with the pole in the barn and also the muons, you can say, well, why can't we think about Stella as being the stay-at-home twin and Terence as the traveller? Wouldn't that mean that in that case, Stella's the one that ages and Terence is the one that hardly ages at all? So in other words, you think of Stella's frame of reference as the one on board the spaceship and think of Stella as stationary throughout the whole experiment. Well, that's where we resolve the paradox, because actually the roles of Terence and Stella are not fully symmetrical. Terence remains in the same reference frame throughout Stella's journey, so that's indicated by this vertical line here. The world line of Terence, as we call it, and that's something that comes up in the advanced higher syllabus, the world line is just a vertical line in Terence's frame because he stays in the same place all the time. But there isn't a single inertial frame of reference, a frame of reference corresponding to constant velocity motion, that we can put Stella in for the whole outward and inbound leg. Stella has to change frame. I mean, there's nothing more going on than you can't go to Pollux and back at the same velocity. You've got to change your velocity because you've got to turn round and come back again. So that means that there's a minimum of 2 inertial frames needed to describe Stella's journey. And that's what breaks the symmetry between the 2 twins. Now there's more detail. I think I'll maybe leave this and people can have a look at the slides in their own time if they want, or I'll be happy to answer questions. But you can unpick this a bit more in terms of light pulses that you send from each observer to the other one. Terence sends messages to Stella, Stella sends messages to Terence, and you can ask yourself when they leave and when they arrive, and the main point is that if you send them at equal intervals in one frame of reference, they won't arrive at equal intervals in the other frame of reference. So let's skip the details because I've taken more of your time than I planned, but just look at the figure. If you look at the diagram, you'll see that the arrows are not equally spaced. If they are equally spaced along Stella's trajectory, then they don't arrive equally spaced in Terence's trajectory. And if they start off equally spaced in Terence's trajectory, then they don't arrive equally spaced along Stella's trajectory. This is all to do with this problem of defining what you mean by simultaneous in the 2 frames of reference, or actually in this case in the 3 frames of reference minimum that we need. Essentially it all starts to go a bit pear-shaped round about the turnaround, and some people think that means that you need general relativity for it. Well, technically you do, because it's an acceleration, you're changing your velocity. But in some ways you can still understand what's going on or think about what's going on just using the ideas of special relativity, because what you can do is you can make that turnaround as sharp as you like, so that the trajectory of Stella is just a diagonal line, and then she instantaneously switches to another diagonal line. The point's still the same. There isn't a single frame of reference that will describe all of Stella's journey. You need at least 2. You need one to get her to Pollux, and you need one to get her back. And because of this breaking of the symmetry between the 2 twins, that's where the time gap comes in. That's why Terence ages so much, while Stella doesn't. So that's the twins paradox. Not really doing it justice. It deserves probably a longer explanation, but I did want to say something about it. So that's basically it. And if I've left you feeling completely overwhelmed by all this relativity, then I very much share your pain. Einstein once remarked that the hardest thing in the world to understand is the income tax, but you know, that's Einstein for you. I think if nothing else, that convinces me. I'm glad I'm not an accountant, but I think I fully accept that a lot of aspects of special relativity, they might not involve difficult mathematics, but they do involve very subtle physical ideas. And as I said a wee bit earlier, if you're struggling with all of this, I can heartily recommend reading How to Teach Relativity to Your Dog. It's a really good book, and it's pitched, I think, at a very good level for discussing this with higher and advanced higher pupils. So thank you very much. I hope I've not taken too much of your time, and if you can stick around in the session, I'll be very happy now to try and answer any questions or comments that people have. Thank you.
I'd like to thank Martin very much for giving up his time to not only to do this, but to prepare for it as well. Now, we will be around for a little longer, so if you put your questions up through the chat pod, that would be much appreciated. And if you can feed back to us either through the chat pod or by email to myself, and I'll collate them. And we may send you a evaluation link out in due course. We'd really like to know how it was. And if you can also indicate if you're up for coming back for general relativity as well, we'll gauge.
Yeah. I've now got a better idea of how much one can cram into a 40 or 45 minute talk, and I think the short answer is a bit less than what I tried to do today. So there was a wee bit of time dilation in my presentation. So again, I know we're after 5, but very, very happy to, yeah, someone's saying talk faster. That's Steph saying talk faster, time expands. But again, I hope I didn't blather on too rapidly, because it takes a bit of effort to absorb all this stuff, and for me to think of what I'm going to say next. So I will now, as I say, endeavour to answer any questions or comments people have. Nick, I would say use both. I think the key here is getting them used to thinking about things from more than one frame of reference. So the argument is time dilation in our frame, because we see their lifetime as dilated compared with the lifetime they would have in their own frame of reference, but the muons make that journey, successfully make that journey, because from their point of view, it's length contraction that makes it possible. As I tried to say, you really do need both. That's a really good question, Steph. I think I would say yes in principle, but I think what that requires enormous care by the setters, and I'm actually on the advanced higher setting team this year, so I'm very sensitive to this issue, is to think through exactly that point. Can it be done from either frame of reference? Now, when we set exams on this stuff, a bit more advanced material for our undergraduate classes on relativity, that's exactly how we approach it. We say, well, you should get the same answer. The student should be able to think about this from either frame of reference, and we try to make sure that the wording is absolutely watertight so that there isn't any ambiguity. We're always careful to define things in terms of which frame we mean. So all I can say is I shouldn't say anything that would give you the remotest hint of what might be in the advanced higher paper, but let me just say that this is an issue, were it to be an issue relevant to an advanced higher question, that I would be absolutely on top of. I'd be trying to think, well, how will a student look at that if they're having to switch frame to do it? If I may be allowed to bring up something that, well, a little bit of kind of dirty laundry of SQA, there was an early version of the equation sheet, you might remember, that had the T equation and the L equation in the same form. In both equations, the square root factor was on the numerator. And it was all down to a misunderstanding, I think, on what was the dash frame and what was the undashed frame. Now, I jumped on this right away. I sent a very long email to Sputnik at the time. I've probably still got it, and it might be useful if I dig that out. It's not that there's a problem to address now, because the equations are now in the correct conventional form on the equation sheet. But the point I was making at the time was that unless you carefully define what you mean by the dash frame and the undashed frame, then actually it's quite legitimate to put the equations in the other form. But as long as you're careful to define which is dashed and which is undashed, then they should always come out that, you know, T prime equals T over the square root term and L prime equals L times the square root term. So, do you mean, Steph, how long does it take? Yeah, how long does it take Usain Bolt? Okay, so that's not too different from a question that we might have asked in our undergraduate course. That's for first year, and that's kind of overlapping, or will begin to overlap now with what's done in the higher. So we're going to have to revisit what we teach in first year to catch up a bit in a few years' time. So, as you say, the time measured on Earth is 9.58 seconds. Is it a simultaneity issue about the start and finish lines? Yes, exactly. I mean, that's, I'm always a little bit uncomfortable about questions that just involve plugging numbers into the time dilation formula without being really clear about what the events are. So, did the events happen at the same time in this frame? You can make a statement about that, but as I was trying to explain with respect to the pole in the barn, that means that they didn't happen at the same time in another frame. So, there's a kind of physics answer to the question, which is along the lines of what you've already typed, that yes, there is a simultaneity issue. The kind of political answer is, well, frankly, to do it really properly, you need to consider what's called the Lorentz transformation, which is Einstein's version of the Galileo transformation. And, I'm pleased that that hasn't been put into the higher, because I think that's just a step too far. It's a bit too complicated. So what we've tried to do in the higher is look at the time dilation formula on its own and the length contraction formula on its own, while at the same time noting that you shouldn't really consider one of them on their own without thinking about the other. So you shouldn't consider issues about the time between events without also asking if there are issues about the distance between events. So Usain Bolt, how does that relate to him? If your toss is the start line and Usain Bolt crosses the finish line, then that will be seen by someone in a frame down here on Earth that's in the same reference frame as the Olympic track. That will be seen to happen at two distinct times. But when you transform to a different frame, then the observer in the other frame will be able to make an observation of when Usain Bolt crosses the start line and when Usain Bolt crosses the finish line, but only by thinking about both the time interval and the length interval can the two observers in the two frames really tie their observations together. So I think it might be worth my while taking this to Sputnik again. What I'll do is I'll try and have a think about how it would be appropriate to phrase the question that avoids this problem of the relativity of simultaneity, because you can, a bit like what we did with the muons, you can think about the question of time dilation separately from length contraction. It only becomes a paradox when you try and flip things round, because after all you could say, well, Usain Bolt, he's the stationary one and he's seeing the rocket go past, so it should be time running more slowly on the rocket rather than the other way round. Well, I'm not disagreeing with that, Nick. In a way, that's why I'm saying the political answer is that we've avoided the Lorentz transformation precisely so we can just set questions that involve pupils plugging numbers into an equation. The onus is then on the setters to make sure that the wording of the question is not ambiguous, that the wording doesn't mix together measurements made in one frame with measurements made in another. And that's what I think I can perhaps clarify via a Sputnik post. I'll try and get onto that in the next few days, because you can word it in such a way that you avoid that ambiguity. But if you introduce that ambiguity, then it's not just confusing, it runs the risk of just being plain wrong. So that is the challenge. Unless you're going to go the whole way to the Lorentz transformation, which I totally agree you should not do in the higher, then the challenge is making the questions clear and simple and unambiguous so that they've just got to plug numbers into a single formula. So I mean, if people can find examples of questions in past papers that they regarded as ambiguous, well, you might well be right. Not on my watch, so to speak, I might say. I would like to look at them, and indeed that's again where perhaps I could comment either in Sputnik or in a future session on how to resolve that ambiguity. But I am absolutely not arguing that we should make the questions more complicated. On the contrary, I'm arguing we should make them, in essence, easier by making sure the language is unambiguous. Yes, that's a good point, Stuart. The travel time of the light to the distant observer usually what you're having to assume is that the travel time would be the same from all points in the object. So if you're talking about, you know, Usain Bolt running his 100 meters, you're sufficiently far away that you can ignore the difference in light travel time from one end of the track to the other end of the track. But believe me, you're into all sorts of deep territory if you don't take care there, because there's some wonderful examples of the weirdness of relativity here as well, where you can kind of see round corners when you've got a moving object, because when you also allow for the different light travel time, then the shape of objects distorts as well. So you don't just get length contraction in one dimension, but you can get a distortion of the shape in multiple dimensions. Yeah, good point, Nick. I think you know, I'm glad to hear that you're reasonably happy that the past papers have avoided these pitfalls. My personal view is, this is why I like Chad Orzel's book so much, that there's a lot of stuff out there that is taught in liberal arts colleges in the US as part of like Physics 101 or Astronomy 101 courses, and I think sometimes they cut some corners. In fact, the L prime formula that was wrong in the very first equation sheet, I don't know who it was, but I remember talking to someone in SQA and they'd found it in one of these astronomy liberal arts college physics books, and they actually did have the equation wrong. Well, at least they didn't explain properly what frame they were in. So I think there is a danger in going to some of the support material. That's why I think there's a role for the likes of me and my colleagues, you know, to sort of really take on the responsibility for making sure that we're not putting stuff out there that's just going to add to the problem by leaving all the teachers and pupils scratching their heads. Just over a year ago, I was invited to go over to Norway to talk to them about what we're doing with the CFE higher and advanced higher in relation to relativity. They're thinking about something very similar in the Norwegian physics system, but actually they are planning to write a textbook. And I suppose you've got to say that that is one advantage of having a textbook, is as long as you're sure it's correct and as long as you're sure it's unambiguous, then everyone's singing from the same hymn sheet. I mean, in other ways, I'm quite a big fan of the idea that we kind of grow the material organically and stuff comes through, you know, the pixies and so on, but it does mean that you run the risk. It's a bit like Wikipedia. There can be stuff out there that looks correct and looks really useful, but it actually isn't, and you know, not everyone can spot that at first glance. Sometimes I miss it as well, but I'm certainly always happy to take a look at things that people have found and to comment on whether I think they've got it right.
Well, I'd like to thank Martin once again for that. I think Steph's last comment, where he could have chatted all night, maybe applies to a number of you, but and it's a testament to Martin, and indeed the way the higher education community as a whole have been so happy to engage with us on our terms on this. So it's very much appreciated. So hope we'll have you again at some meet soon. Big thank you to Alan Purvis over in SSERC, who is into injury time now, having run the technical side of all of this from Dunfermline. Couldn't have happened without him. Many thanks, Alan. I'll see you tomorrow at work. So,
thanks, folks.
Good night.
Thanks everybody. A lot. Thanks, Gregor, for organising this. Look forward to talking to you again soon.
Right.